physics at all. Doesn't the quarks are all charged. This is their charge, it's plus 2/3 or minus 1/3, depending on whether you're an up-type quark or a down-type quark here. So they feel the E and F force, all of them do. It's only those quarks that feel the strong force. So now this is the difference between my leptons and my quarks, between leptons over here and quarks there. These do not feel the strong force, and these do feel the strong force. So when I talk about the strong force and everything it can do, everything talking about nuclear physics, that's got to be only made up of quarks here, because these things don't feel it at all. The weak force is what's left. Every fermion feels the weak force. So all these guys will feel the weak force, which means then the neutrinos, because they're not charged and they have no color, no strong, no E and M, they only feel the weak force. And that's why we don't know much about them. It's just going through life, right? That's why you can't think of, well, what are they, what do they do? They don't really do much of anything, because they don't interact with anything. Remember, the electromagnetic force is everything that you do in daily life. Anytime you touch anything, anytime you feel anything, see anything, that's all here. The strong force is what's holding all of matter together in the first place. And that has a lot of consequences for all this stuff. The weak force, by itself, is not something we normally interact with. It does important things, which we'll get to. But really what the weak force is able to do is move you back and forth between these different rows here, the top row and the bottom row. That's what the weak force does. It can take you from here to here, it can take you from here to here. But I've got now really 3 different kinds of particles. Particles that feel everything, each of these 3 forces. Particles that only feel the E and M and the weak force, and then particles that only feel the weak force and nothing else. So because neutrinos, for example, only feel the weak force, they're produced in nuclear reactions, they're produced in the sun, and there's this huge stream of neutrinos, gazillions of neutrinos that are flying from the sun at us all the time, and they come right through, and they come right through us, and they keep going. They go right through the Earth, they come right back through the Earth. It's, there's nothing for them to interact with except through the weak force. The weak force is so weak that it very, very rarely happens, which is part of why it took a long time. It's part of why there's like 3 Nobel Prizes there that were just for neutrinos, weakly interacting particles. Okay, so now that we have here. Yes?
That's why you said some of the particles are within the atom and other particles are outside the atom?
Right.
And how do you guys discover the weak force?
The way it was, the first way to discover the weak force is that it's what allows you to go from here to here, to change one of these into one of these other ones. And when you see that change happen, you say, well, there's obviously another force.
Something producing the change.
You see the change happen, you say there must be some way that change can happen.
How.
Because there's no way the change can happen with these 2 forces. You need another force. You need some other interaction to allow one of these things to change into
Is
one.
there particular evidence that the weak force exists, or is just a induction from this change happened, therefore must be something?
No, it's very strong evidence of the weak force.
Okay.
The way the neutrinos we first figured out they existed is because we had a couple things crash into each other, and then something flies off. And you know from conservation of momentum, if I have things crash in, they have to fly off with equal momentum. And so there's missing momentum. Something was going off this way, and there's got to be something balancing it off here. I can't just be walking a straight line and suddenly make a turn without hitting something. Something has to fly off in the other direction. The something that flies off in the other direction was the neutrino. And you know, what to call it, what it was, that was ambiguous for a while. But that was the initial idea. There's got to be something there. They drove all that. Okay, so. Yeah.
Sir, could you say something about the lifespan of these particles?
Yeah, particles will decay if they can. And if they can means if they have enough energy to, and there's something for them to go to that's allowed. So these guys are heavy and decay very quickly into these other ones. The lifespan of an electron and, let's say an up quark are, because they're the lightest, there's no place for them to go, they don't decay. So the heavier something is and the more ways it has to decay, the faster it will decay. That takes more relevance when we start talking about composite particles that are made up of these things. That's why the proton, for example, the proton does not decay, but the neutron does. The neutron lives 15 minutes. As I get bigger, heavier things with more energy in them and more choices for how to decay, then the lifetimes get shorter and shorter. And one of the ways we know that whether something is using the strong force or the weak force to decay, and part of the discovery of the weak force, and actually the discovery of the strange quarks as well, was because of the lifetimes were wrong. The lifetime should have been much faster, but there was a prohibition on the decay because it could only go by the weak force and not through the strong force, and that made it take longer. So hopefully we'll see that. Okay, now this two rules here that are important. One is, it's called conservation of lepton number, or independent conservation of lepton number. So I have these three generations of leptons. And there's a rule that says I have to end up with the same number of leptons I started with in any interaction. So if I have a bag and I've got three of them, at the end I've got to have three left over. And anything I do, that's a fundamental rule of what happens. More than that, it's not just that I need to have a certain number of leptons at the end as I had at the beginning, they have to be the same kind. So that's why I need three different kinds of neutrinos. If I have an electron at the beginning, I can have either an electron at the end or a electron neutrino at the end. If I have a tau at the beginning, I can have some combination of tau and tau neutrinos at the end. But I can't start out with a tau and end up with an electron neutrino. So whatever I start out with, I have to end up with the same number. That's conservation of lepton number, or independent conservation of lepton number. That is one of the things when I say, if it's allowed to, it'll do it. That's one of the restrictions on what you're allowed to do and what you're not allowed to do. The other thing is that because I can't have a quark by itself. I can't have something colored by itself. What that means is I have to have if I start out with something that's got three quarks, I have to end up with something that has three quarks. Because I can't make something from three go to something with two because then I have one by itself. And if I do that, then I would have something with color by itself, which I can't have. So the number of particles with three quarks has to be the same at the beginning and the end. A particle with three quarks, these things have names. This thing is called a baryon, and this is called a meson. So that's what I have here. I've got the baryons with three quarks and the mesons with two quarks. And these are things that are made up of these various quarks. So once I have this idea, I can start making stuff. Because now I know what the interactions are, I know what the rules are, and I can start piling these things up and make things. The first thing I can make is a proton. I have plus 2/3 here, plus 2/3 here, minus a third here. That's electric charge. So my E and M charge on this is +1. These things have spin. If this is 1/2 up, 1/2 up, 1/2 down, then I'll have spin 1/2 up for this. So then my spin is 1/2. And this looks a lot like a proton. Now there's other things I can do. Before I get to this, talk about the standard model and how fundamentally important this picture is. We have placemats that in grad school you eat off of. Or standard model placemats. So if you get the new ones have a few extra things in here. They had the Higgs, which wasn't on the placemat that I had in grad school. A number of other minor changes in there. But people have this thing hanging up in their living rooms. This is the wall art for physicists, and, especially at an undergrad level when all this stuff is fun and cool. So it helps drill it into you. So I can make a proton. I can make, let's see, I can take two of these, and up. Now what do I have? I have plus 2/3, minus a third, minus a third. That's neutral. This is a neutron. So here's my proton, and here's my neutron. Now, we'll get to in a few minutes why the story is more complicated than this. But for now, this gives you the idea of how you make a proton and a neutron. Got a lot of other stuff I can make. I have all these other quarks I can make. I can put them together in different combinations. I can have an up and an anti-down. I can have a down and an anti-up. Okay, these are going to be mesons. I can go on and on and on and make lots and lots of different particles. If you start looking at how many you can make, it is hundreds and hundreds. It's like 216 different combinations you can make by mixing just the baryons, just 3 of these together. And for the mesons, there's also hundreds I can make, but it's more than that. The reason it's more than that is not only do I have a proton I can make, but I can add energy to this. I can get it excited. In the same way that we had atoms, where I had an electron in one shell, in one state, and I could add energy and put the electron in a higher state, I can do the same thing here. I can get this thing excited and create a higher energy version of this particle. Now, in an atom, it looks very similar. It's the same atom, just with more energy, because the atom is a simple thing. The electron just moves up and down from one orbit to another. When I get to these baryons, when I get to these particles, there's more complication in what they can do, and so the particle actually looks different and starts behaving differently. I can get different spin in the thing, I can get different amounts of energy in it, and it will behave in different ways, and because it has more energy, it can decay into different particles. So I have this zoo that starts.
Question. So you have multiple protons in an atom. Can they have different contents?
Every proton is the same as every other proton. And when I say the same, I mean identical, indistinguishable, interchangeable. That's true of all these fundamental particles. There's no way to know which one is which. There is no meaning to which one is which. So I say, well, I'm going to knock this proton out, this proton and that proton and the same proton. I can switch them and it doesn't make any difference. So every proton looks like 2 ups and a down. And they're all exactly the same in that way. So what happens is we get a lot of particles here. And a few examples. It becomes a huge number of particles. It becomes a number of particles that's so big that they have their own phone book. This is the Review of Particle Properties, which is published every year by the particle physics community. And it contains pretty much a list of every particle that you could possibly make out of these combinations. You can calculate fairly straightforwardly, in many cases, how heavy that particle should be, based on the standard model physics here, how long it should live. And this contains for each of the particles what it can decay into, and then what the experimentally measured lifetimes of each of those things are, and what the experimentally measured masses are. So it's really a summary of every experiment in particle physics that's ever been done with each of these different kinds of particles. So every particle is listed here with its name, and then all the different ways it can fall apart. This thing is critically important. You need this like in your day-to-day life. You need it so much that you get tired of carrying it around, and you carry around this one, which is the tiny version for, like, that's probably why these guys are young when they do their work, they can still read these things. So there's a lot more information in there of kind of background of what the experiments were doing, so you can kind of judge, do I really believe this number or not? Because these are experimental numbers. Maybe you believe, maybe you don't. Maybe they were measured 1,000,000 times, maybe they were just measured once or twice. And so this handbook here doesn't have all that background information, but it is a good flip through. You see something and you can figure out what particle it is and what it decayed into. At this point, I'm going to take a brief detour into history, and then we'll come back and see what's actually inside this.
Can you generalize if you take these 12 primary particles,
Yes.
you can use just 4 and the rest can be just this?
No, because the difference they have between them. In fact, it's actually worse than that, because I've got the 12, but I've also got their antiparticle partners. So it's kind of 24 fundamental particles. But these guys have color, which isn't really shown here. So I have red ones, green ones, and blue ones. So I have 18 of these guys, plus the 6 of these, plus the 1, 2, 3, 4, 5 of these, and then the antiparticle pairs. It comes out to something like 61 particles. And that's before I even get to the Higgs. And it is a little bit troublesome. One of the open questions in particle physics is why I need so many particles.
Right.
Maybe you do, maybe you don't. So there is a quest to see maybe it should be simpler. And then there are those that say, this is pretty simple here. This actually the regular even structure, it's so repetitive that there may be a way to derive these things as expressions of some of the other particles potentially. But it's not unpleasing, it's not unaesthetic and that drives a lot of this stuff, to have a structure like this. So people are generally happy, if not satisfied, with this picture and with having this many particles. What we would like to know is why the ratios of masses between them are what they are, and that's part of the Higgs story. But for the most part, people are okay with where we are in terms of understanding that. The other open question, of course, is that all? Maybe there's a fourth generation of quark here. Yes.
Yeah, how could the particles in your directory there named?
Yeah.
I mean, what was the naming convention related to all those?
You discover it, you get to name it, but you can't name it after yourself. And you have to name it something that hasn't already been taken. And that actually creates a lot of constraints, because after a while, with hundreds and hundreds of particles, you run out of names. So when you get to the excited states of particles, a lot of them, they'll have the name, and then there'll be the name with a number in parentheses. So I'll have, maybe the lambda, and then I'll have after that, there might be a lambda, I don't know, 1350 or something, which is the mass of this one compared to what the mass of this one used to be. And I can keep going with that. So sometimes as I get more and more particles, I give them numbers. Sometimes I give them new letters if they're different. The letters can be in English, they can be in Greek. And finding new letters and what they should be named is something that we go back and forth on sometimes. Sometimes you find a particle, you give it a name, and then you find that it wasn't really there. One example, and then you have to take the name back, then you get to use it again later. One example is the upsilon particle. Hard to draw, it's that one. That's the Greek letter. Leon Letterman, who's one of our cast of characters here, discovered the upsilon particle at a certain mass. And it turned out that it wasn't really there. It was just an artifact of the way, it was like a certain percentage chance that he was wrong, or his group was wrong, he was the leader of the group, and it turned out it was wrong. So the upsilon particle started becoming called the Oops Leon particle. Luckily, about another year later, they did find another particle that was a little bit heavier. That one was real, and so that's what we call the upsilon particle now. So, it's also, okay, so
There's one more.
Yeah.
What about Higgs? How does it fit into this?
about 20 years later. The Higgs is what gives the mass to these two particles, and in principle to everything. But for now, that's why these things have mass and this doesn't. One thing that happens as time goes on is I have the electromagnetic force and the weak force. It turns out those aren't really different from each other. It's one force that just has different expressions at low energies. And so the gamma, the W, and the Z are really all the same type of thing. And I need to then describe why the photon has no mass and why these guys do have mass and what the relative masses are and where they come from. And the Higgs field is what gives rise to those masses. So potentially at the end, we'll get to that. But that's the new stuff. But it fits in. It's similar to one of these things. It is a boson. It's a scale. It's not the same kind of boson, but it is basically in that same fashion.
I know you erased it, but when you had that drawing up of the proton and the neutron
Yeah.
over there, is that what you're saying is inside of, for example, if it had one electron going around it, would that be hydrogen?
If one proton with one electron going around it is hydrogen. Yeah.
And the one neutron as well?
There's no neutron in normal hydrogen.
Oh.
It's just the proton and then
Now,
the electron.
can you see with the best microscopes available the proton itself?
No, because the wavelength of the light is like this, and the proton's like this, and so the light will just go right by it.
Oh, so but you can see the nucleus, but you
You can't see nucleus either.
can't see the nucleus
You
either.
can't see electron. You can see an atom because, but only where you have the wavelength equivalent to the size of the atom. So that's why you need an electron microscope instead of a regular microscope. Because the waves on the electron microscope are little, because the electron is much bigger. And big is the wrong word. It's got more energy, and so it's got smaller wavelength. And that smaller wavelength is able to see smaller things. It'll hit them and bounce off, which is what you need to see, instead of just going right around it, which is what normal light will do in that case.
So when does the neutron in the periodic chart, does that start with helium?
Yeah,
That's the
helium has
first
two
element that
protons, two
has...
neutrons.
Oh, okay.
Just, this is a very simple one. When you say the guy discovered a particle and then it was shown that it doesn't exist.
Right.
Like, what does that mean? What
That's
does
next
it
week's
say?
subject. You discover with a detector, and to some extent it's a process of elimination. There's different kinds of detectors where you're able to, in a sense, see the evidence or the trail of a particle. And when you see something you don't expect or something that can't be based on what you already know exists, that gives you evidence that there's something new out there. And that's next week is really all about how we do that and why we're building the big machines. But before we get to next week, we got to get to 1897. This is what I'm talking about really is a folk history. There's a lot more detours along the way, but I'm just going to hit some of the highlights here. Now, I haven't talked much about history overall. I've shown some pictures and said, okay, this guy's that guy. There's a couple of reasons for that. One is that there's a lot of accessible history of science books out there, and you don't necessarily need me to explain to you what, who slept with who or whatever the history of things was. The other thing, though, is that the history of individual physicists in particular tend to break down into personality cults. Einstein, there's all kinds of posters of him all over the place with his tongue hanging out or riding a bicycle or crazy hair, whatever it is. He dressed up for him as a Halloween costume. Richard Feynman is the other guy. His first memoir, which was so popular, he felt he needed to make a second memoir of himself. So surely you're joking, Mr. Feynman. It's a fantastic book. It's a great read, and it's all about him It's all about him, which I guess a memoir should be. But there's a whole personality cult around him of teaching himself to pick locks and playing the bongos and being able to convince native Italian speakers that he speaks Italian, even though he doesn't speak any Italian at all. That kind of stuff really, it's fun, but that personality cult is really not the history of what happened. So I tend to stay away from those stories for those reasons, except where they do come in and kind of influence the direction of things. And it is kind of fascinating, the interaction between all these guys. A lot of the story here is that the different physicists were working together and going back and forth and passing things and not believing one another and challenging one another in different things. But that's that's the story of the history, and in the limited time we have, getting the basics of the physics is really what I hope to convey. But this is a case in particle physics where understanding the history will help you understand why there are newspaper articles about this stuff and why people like me decided as children to go into this. And a lot of that is because it's so recent. We'll take 1897. 1897. Before 1897, nobody knew anything. You knew more by far coming into this on day one, no matter what you knew or didn't know. Or if you never had a science class in your life, you knew way more than anybody knew about anything correctly in 1897. What we did know in 1897 was all wrong anyway. Now, I'm not talking about all of physics, I'm talking about particle, nuclear, atomic physics. The picture then, well, what happened in 1897 is the electron was discovered. And now I've got this electron, which is not an electron in those days, it's a corpuscle. It's a corpuscle of charge. So charge now comes in little packets of some kind, and they're negative, and eventually we decide we'll call these things the electron. But these were not electrons floating around, they weren't orbiting an atom, we didn't have atoms. We had pudding. That's what it was called. These guys were all British in those days, so it was probably more like a bread pudding than anything else. This actually was a plum pudding, because the statement was that you have stuff, chalkboards, ground, you, everything, was a pudding with these corpuscles just sprinkled inside them. And that was what we knew of things in the turn of the century, right around 1900. In 1905, what happened was it was possible to have photons come off from the various processes that happen. Some of the stuff we talked about at the beginning. You see light coming out of things. When something gets hot, like your stove element, it glows, the sun glows, all those things, that's photons coming off of some kind of stuff. And they figured out at that point that the photons came off in chunks. Certain amounts of light would come off. But nobody believed that it was actually chunks of stuff coming off. It was just something in the pudding made it so that the pudding would only release light in certain quantities. Nobody knew why. Then in 1905 is when Einstein came up with the understanding that there should be a photon. That's that photoelectric effect that we've come back to a few times now. This is one good reason why it's the photoelectric effect that he got the Nobel Prize for and not relativity. Relativity is critically important. The photoelectric effect underlies everything that we've been talking about. So Einstein says, okay, we have a particle of light, which later was called a photon, and then the photon was written gamma, because they had gamma rays that were some kind of radiation, nobody knew what it was. When they figured out that, okay, photons and gammas are the same thing, that's when that became the symbol for a photon. So in 1905, Einstein figures out that there are these photons. No one believes him. For 20 years, no one believes him. No one will accept this. This is nonsense. Forget it. Finally, in 1923, experiments were done and figured out that, well, this actually is true. The photon really is a thing, and there's no way around it. And then in 1926, that's when it got its name. That's when it became a photon gamma. In 1930 is when we had antimatter. So we started out with electrons, which people by now had figured out were round. And then there's the positron came out. Most things you would call this an anti-electron, but because of the history, it had its own name. It's a positron, positive electrons. So this is now 1930 for this, and then for the proton, and most things are electrons, protons, neutrons. To get an antiproton took longer. That was 1955. And then they figured out that there must be some kind of a strong force that's connecting these things. Because you get this picture of the nucleus where I have protons, something's got to hold them together and fight this electric charge. And that must be a strong force. And it should be carried by some kind of a particle. And that particle should weigh about some kind of a middleweight particle. It should be heavier than the electron, it should be lighter than the proton. And so let's go look for it. And they went out and looked for it between basically the 30s, the 40s, up to 1950. And they found it. The problem is they found two of them. One was the mu, it turns out. And the other one was a pion, which is an up and a down. That's one of those mesons together. And the two guys didn't agree. They didn't realize there were two different ones in the first place. It turned out they figured it out because one guy was doing his experiments on the top of the mountain, and the other guy was doing it at sea level. And the muons could come through the atmosphere, and the pions couldn't. So the guy at the top of the mountain was seeing the pions, and the guy at sea level was seeing muons. They're about the same weight, so it was kind of hard to tell them apart. But the way you tell them apart is that one of them feels the strong force, and the other one only feels the electromagnetic weak forces. So we have something else. We have discovered our first two particles that is not normal matter. And again, this is let's say 1947. So 1900, I don't know anything. 1930, I figure out I've got antiparticles made up of normal stuff. And then by 1947, 1950, I found a couple of things that should not have been there or that we didn't know about that don't make up normal matter. And then, it's also around that time that we figured out that you had to have a neutrino. The reason was because when the pion, or actually when the muon breaks up into pieces, that's where the missing mass was. There had to be something there. And that something must be the neutrino, so we figure, okay, we gotta have a neutrino. And that was 1950, and in 1956, they actually found the neutrino and said, okay, this is confirmation there's a neutrino. We didn't have three kinds at that point, we only had one. But we had neutrinos. So here we are, so I've got a neutrino, I'm in 1956. And that's it. I don't have a whole lot else. Then what happens is particle accelerators show up. And I can start smashing things together. And I can take two electrons and smash them together, which means I've got a lot of energy now. I need two things for a particle accelerator. Well, basically, what has to happen is I need stuff going fast enough that I have enough energy in it that I can make new particles. That energy can turn back into matter. So now, 1947, basically all hell breaks loose. Yep.
Now, you would think that building the atomic bomb in the 1940s, early 40s, there would be more knowledge of some of these other particles.
Everybody who did all this work and who was needed to do this work was busy doing that work. So there was a lull. There was a period of a decade or so where not a whole lot of progress was made here. And then when everybody came back, that's part of why things also exploded starting around 1947. Exploded. It didn't explode. The other thing that